All right, welcome to lecture number 5. And in today's presentation, we'll be looking at system characteristics and stability. And in this presentation, we're going to be looking at system response characteristics, first and second order system response, steady state error, poles, and zero analysis. And if time permits, we'll look at system stability and we'll examine the root Howitz stability criteria. All right, so let's get started. So when we talk about a system response, we are talking about how will the system output behave in response to an input to the system or a stimulus or some input to the system. Okay, so if we bring our attention to the diagram here, and we are looking at a block diagram representation of that system. So in that box, it represents a system, and a system that has a unique characteristics. All right. Now, when we speak about system response, we are going to stimulate the system. We're going to put an input to the system, and then the question is, how will the system respond? Okay. Now, to discuss the whole concept of system response, we're going to look at a typical system response to an, or should I say, to a step input. Okay, remember what a step input is. We are moving from 0 to 1 and maintain that value for infinity, mathematically speaking. Now, here we're going to examine some of the features of a step response. So here is the input command. The input command is a step. All right, it's a step. And what is the response of the system? The response of the system is shown with the blue line, all right, with the blue curve. And we can see that the system was initially at some point, and we could say it's 0 for the purpose of the discussion. It is at 0, all right, so I'm going to label here as 0. And we see where the system gradually begins to increase and more, should I say, drastic increase as we go along, and then it tapers off to a flat position, or it settles down to a position. Okay, so we're noting the response of the system's output. Now, there are some parts to this response that are very important. All right, and we often in control systems theory and discussion speak about system response, and we said the system response has 2 parts. And the 2 parts to the system response would be transient and steady state. Okay, so transient speaks to the part of the system response where the system is now moving from some initial point and now attaining some new point. So during that time, right, we see the system is in transient. It is in transient. I will call it the transient response. So that portion of the plot is referred to as the transient response. Now, once the system has gotten to a point where there is no significant deviation, we say the system has settled. And now I must point out that even though in this particular diagram we're seeing that the system has settled, there's no movement in the system's output. There are going to be times when the output is not as quiet as it is here, or it is not settled at a fixed point, but it may settle and be having this steady variation at the end. Long and short, 2 parts, system in transient and when it actually settles down to. Now, what we'd see here before we move on is that there's a descriptive term here, steady state, which we'll discuss a few slides down. We'll talk a little bit more about what that means. Now, for us to appreciate and use system response, we have to understand that it is a system response that we use to describe the nature of a system. We describe the characteristics of that system based on how it will respond. And what we're going to find is that we can use the model of the system to also characterize its response. So in one sense, we can say, okay, let us see how the system responds to a stimuli, and then from that response, we characterize it. Or we could look at its mathematical model, and we can pick certain important parameters from that, and then also characterize its behavior. So let us look, first of all, at the system response characteristics. So what we're saying is that the performance characteristics of a control system are specified in terms of certain terms, all right? The transient response terms, yes, and the steady state response terms. And in particular, we look at the system response characteristics in terms of the response to a unit step input. Yes, so all of these terms that we look at, yes, we are looking at the system response specifically due to a unit step input. Now, here are some of the commonly used terms in characterizing a system response. We could talk about rise time, and that's abbreviated T subscript R. We could talk about the peak time, that's T subscript P for peak time, settling time, T subscript S, and maximum percentage overshoot, M subscript P. Right? These are some of the more commonly used characteristics terms, or terms used to qualify or to describe the characteristics of a system. Now let's define these terms. Start out with the rise time. So rise time is the time required for the response to move or to rise from 10% to 90% of what we call steady state. Okay, from 10% to 90% of steady state. In other words, 90% of the journey to steady state to 90%. That difference in time between the 10% and the 90% is the term that is often described and used for the rise time. Okay, that's rise time. Now, peak time, T subscript P, this is the time required for the response to reach the first peak of the overshoot. And this is provided the system actually has an overshoot. Okay. Now, for settling time, T subscript S, this is the time, sorry, required for the response curve to reach and stay within a range about the final value. Yes, and it is specified by an absolute percentage value, and this could be for 5% or 2%. So once it gets and stays within 2% of that final value, yes, we say it as settled. So in some instance, the steady state value that is used is 5%, in some cases 2%. Okay, in MATLAB, all right, and you by now I believe would be exposed to MATLAB. When we derive step responses in MATLAB by default uses the 2% settling time. So that's the time it takes for the system to get within 2% of its final value and stays within that margin. Okay, and that's the settling time. Maximum percentage overshoot, M subscript P. This is the maximum peak value of the response curve, and this is measured from the steady state value, yes, and it is expressed as a percentage of the steady state value. All right, how much did you exceed your steady state value? That is basically what we're saying, the maximum overshoot. Okay, maximum point at which you went, the system response went above the steady state value. We're going to look at these terms, peak time, rise time, settling time, and so forth, in terms of two types of system response. You're going to start out with the response of the first order system. Okay, first order system response. Now, what you're going to find is that the response of first order systems have a consistent shape. whereas it may vary, but there's a consistent look, there's a consistent shape to the response of first order systems. What you're going to find is that the response will look like that of the charging of a capacitor. Okay, all first order systems behave in that very same way. Now, if you look on the plot here, we're seeing that this is a first order system. It looks like that of the charging of a capacitor. And I'm going to bring your attention to the general form of a first order system. All right, that's it. G of S is equal to K over tau S plus 1, where K is the system gain and tau is the time constant. Okay, so what am I saying here? I'm saying to you that all first order systems can be written in this form. Okay, the transfer function can be written in that form. And note that the highest power in the polynomial is of the order 1. Highest term is of the order 1, s to the 1. All right, so you can recognize a first order system by looking at the polynomial in the denominator. And we're going to speak a little bit more about that very special polynomial. But for now, bear in mind that this is the structure of all first order systems. So there exists a number k, there is a number t, or should I say tau, sorry, that represents the system gain and the time constant respectively. Now, for first order system, the settling time is approximately equal to 4 tau. And note the side that I have 2%. So I'm talking about the 2% settling time. It's approximately 4 tau. Okay, so if we should look at the plot here, remember we're talking about the step response due, the response due to a step input. Okay, so a step input is what was used to generate this response that we're looking at here. So if we were to say, okay, we expect the system to go to 1, yes, and let's see, if it's of that nature, then we expect that the 2% settling time will be 2% of 1, and so that would be 0.02, which means that the settling point would be 90. The point at which you begin to set is 90.98, sorry, 0.98, all right, which means that you are 0.02 away from the final point. So basically what I'm saying to you here is that the 2% settling time is when the plot gets, yes, to the 0.98 position and stays in that point. Okay, and it occurs roughly at about 4 tau. All right, 4 tau. Now let's look at the step response for a second order system, and I am using this particular response here just to describe the terms that we looked at earlier. And what you will see in subsequent slides, presentations, is that the response of a second order system can have a number of possible shapes. And we're going to see that there are fundamentally 3 possible shapes for the response for second order systems that are stable. All right, using the word stable here, we'll discuss that also. So let's start with the rise time. And the rise time here is defined between 10% and 90% of the final point. And so we're talking about the time that is here between the two lower and upper limits, okay? That's the rise time, okay? Rise time. Now, let's look at the peak time. Peak time is the time taken for the system to reach the first peak of overshoot. Here is the first peak of overshoot, and the time taken to reach that first peak is here, TP. We could also speak of the settling time, right? So the settling time is the time taken for the system response to get and stay within a certain margin of the final value. Now here, I hope that you'll see that based on the numbers here, we are using a 2% All right, settling time criterion or criterion. All right, so here it is. Once the system gets within the margin, so let's look at the margin. The margin is defined by these two limits here. I'm not going to be able to mark too much on this. All right, these two horizontal lines. The middle one is where it actually settles. Now, would recognize that the system actually enters the region here, not the first time, but it enters here and it leaves here. It enters here, but you could say from this point, it does not leave. Hence, the first point at which it enters the margin and stays in the margin is referred to as the settling time. All right, so the settling time would have been defined appropriately as shown here. Okay, go ahead with your question, Adam. See your hand raised, Adam. Go ahead with your question. All right, we're not hearing Adams. So we're going to continue. We want to now look at the general format of a second order system, and this is what we're looking at right here. So all second order systems can be written in this format, right? So that's k omega n squared all over s squared plus 2 zeta omega n s plus omega n squared, where k is system gain, zeta damping constant or damping ratio as you'd see in some material, omega n is the natural frequency of the system. And so those are the terms defined in the expression. Now, the characteristics term, settling time and peak time, as you have them Ts and Tp respectively, defined as such. So Ts is 4 over zeta omega, and it's usually expressed as approximation. So you oftentimes see it as an approximation, okay? It's approximately equal to 4 over zeta omega n. That's the 2% settling time for a second order system. And the peak time is defined as pi over omega n times the root of 1 minus zeta squared. Okay, so these are just some of the formulas associated with the characteristics term for second order system. Now, before I go to looking at the 3 major design objectives, I would perhaps want to, let's do this here. Let's come back here for a second. Let's look at a second order system, and we're going to try and extract the values from this system. So if I have here g of s, hold the screen a little better. If I have g of s is equal to 5 over, let's do this like this, 5s plus 25, let's put square here, s plus 1, all right? What is k? What is zeta? What is omega n? Can we establish what that is? All right, so we agree that this is a second order system because the highest term in the polynomial is of order 2. All right, go ahead with your question, Joel.
It's not a question, sir, but I was going to answer the question that you asked about what is the natural frequency and
Okay. All right, please go ahead.
so the natural frequency would be the square root of 1 divided by 5, 1 over 5, root 1 over 5. How much is that? Root 1 divided by 5.
Okay.
Start with
All right.
0.
That's fine. You know, you can leave it as such. Omega is 1 over root 5.
Yes, sir. And
And
we
you want
can
to tell us
use
why
that.
you,
We can
I'm
use
sorry, I'm
that to
sorry, I'm sorry,
find.
I'm sorry, I'm sorry, Joel. Could you tell us how you arrived by that?
Well, based on the general expression and
Mm-hmm.
the g of s that we have, the transfer function that we have,
Mm-hmm.
we can note that the coefficient of the s squared term
Mm-hmm.
needs to be divided right through. So if we do that, we could get the omega n squared aspect of the equation, and then use that to find the natural frequency. Then if we have the natural frequency, we can find what is the gain of the system by um, squaring the natural frequency and dividing 5 by it. So it would be 5 divided by 1 over 5, which is basically multiplying 5 squared. So k would be 25. And
Mm. All right, hold a second. Let's go it one step at a time. So here, what I believe you're saying is that we need to have the expression looking exactly like what is here. And
yes,
what is
sir.
required is that the coefficient of s squared, or the s squared term, must be
1.
equal to correct. And so to achieve that, you have to divide throughout by 5. That means to divide the numerator and the denominator by 5. And so in so doing, you end up with a new expression. When I say new, not meaning different, but having resemblance to the general format of the expression. All
Yes,
right, so
sir.
that would be, if I'm just going to write it back here, I'm sure the others can go through. So it would be equivalent to saying 1 over s squared plus 5s plus 1 over 5.
Right.
And hence, if 1 over 5, and if we can know what we say would now equate coefficients, okay? So the coefficient of s squared is established as 1, the coefficient of s is now 5, which simply means, if I could come over here, please, is that 2 zeta omega is equal to what? 5. That's a fact based on the coefficients here being matched to here. And we also know that omega n squared is equal to 1 over root 5, which is what you were saying earlier, right? I'm
Yes,
sorry,
sir.
not 1 over root 5, but 1 over 5. I'm sorry, 1 over 5. My apologies on that. 1 over 5. And so to find omega n, you just simply root 1 over 5, 1/5. That's what we're doing here. And you can now substitute that over here to make zeta the subject.
Yes,
All
sir.
right. So we could see that zeta, you could let me know if I'm on the right track here. Zeta would be equal to 5, and run out of space, divide by 2 times the root of 1 over 5. All right. And so we weren't asked for zeta, but well, yes, in fact, I did ask you for zeta. See it here. All right, zeta. And going to the numerator now, we would recall that k. Let's look focus our attention on the numerator here. So k omega n squared is equal to what? Based on what we have here, it's equal to 1. K omega n squared is equal to 1. So what is k? All right, that omega n squared is equal to 1 over 5. So therefore, k will be equal to 5. Is that okay? All right,
Yes,
k
sir.
is equal to 5. All right, so it's not difficult to manipulate the expression to extract certain important parameters. So if it is that you were now to uh, determine the settling time, all right, you would now need to take that function and extract the terms of zeta and omega n. All right, and then you'd be able to determine the settling time without actually seeing the um, the actual response to the system. Can do the same thing also for the peak time. So we could determine the peak time as well just by looking at the transfer function and extracting the pertinent or the relevant coefficients or terms. Okay. All right, so let's continue. We're now moving on to system response, and we're still looking at system response, but right now we're trying to tie that into the whole reason for us wanting to get a system response. And remember, we're talking about using models and using simulation software. Okay, so three important design objectives. All right, once you're going to design a control system, then we could say here are the three fundamental objectives that need to be met. One, you need to produce, yes, a response that has minimum transient duration. Right? You want to produce a desired transient response. That's the whole story. We want the system to have a desired transient response. And in summary, that is it shouldn't take forever. All right? It should do so in the minimum time possible. That's what we call acceptable transient response. Secondly, we want the system to settle with minimum error. All right. So we want to reduce steady state error to zero if possible. All right. Now, in reality, it never ever goes to zero. It's as close as possible, but in reality, it will never ever go to zero. All right. So we would have our error being maintained at the minimum possible, or the minimum that is suitable for the situation. Thirdly, which it should, to be truthful, encapsulate both one and two, the system must be stable. Okay. So these are the three design criteria. And we're going to look a little bit at these as we go along. So let's look at steady state error. And we would have seen steady state error in that first response plot, which you may not remember, but it's fine. Steady state error is the difference between set point, as where you desire or where you command the system to go, and where it actually goes, steady state output. So steady state error is the difference between set point and steady state error. I should have a plot here to show that. Not yet. So a control system, that's response error. A control system should respond to the input command. Remember that when you give the system a command, it should respond. All right. And so the system should respond to an input, or the system should respond to a disturbance. All right. So remember, when you have a closed loop system, the system should work to keep the controlled variable or the output as close as possible to the set point. So therefore, if it is maintaining the set point, let's say for argument's sake, you're controlling a drone and the drone is now hovering, and you set the drone to hover at say 100 feet above say sea level for argument, to keep it simple, 100 feet above sea level. That is what you set the set point to be. Now, if a gust of wind should disturb the drone, what would you expect? Well,
Well,
if it's closed loop system, go ahead, please.
I'd expect the drone to return to its original position, or do the calculations to return to its original position.
Yeah, it should attempt to do so. You know, that's what at minimum attempt to do that to recover its original position. That's correct, right? So the drone should now recognize that it's been disturbed from its desired position, and now should seek to retain or regain that original or that set point, right? So it's now responding not due to a new input command, but it's responding to a disturbance. Okay, so closed loop systems are supposed to behave in this way, respond to a new input or an input, and also responds to any form of disturbance. So the system should bring the control variable to the desired or set point, and it should also bring the control variable back to the set point after disturbance. Now, systems are usually designed to have tolerances of 5 plus or minus 5% or plus or minus 2%. All right, and that varies. It depends on what system you're designing. In some cases, it could be much bigger than that. All right. Now let's come back to the steady state error, and here I'm highlighting for us the steady state error point, or the point at which we can evaluate the steady state error. Now you'll notice that the input command is one. It's a step input, unit step input, and we're seeing that there is a deviation between where the system settles and where the command is. And so that would define our steady state error. Okay, and remember there are two parts to our system response. We have transient, which is on this side, and beyond this side, all the way back here, we'll have steady state response. We're now going to take a look at two important terms that help us to understand the behavior of control systems. Very important terms. Excuse me. And the terms you're going to look at are poles and zeros. All right. Now we're going to define the term poles and zeros right now. So the poles of a transfer function are the values of the Laplace transform variable s that cause the transfer function to become infinite. All right. So any value of s in that you can find. So that's when you actually put it or substitute it in the transfer function. In so doing, if the system tends to infinity, then we refer to that value of s as a pole of the system. Now, for zeros, the zeros of a transfer function are the values of the Laplace transform variable s that cause the transfer function to become zero. Therefore, any value of s that you can find, that when you substitute that value into the transfer function becomes zero, then refer to that value of s as a zero of the system. Let's expound on that a little bit. So here, I want us to focus our attention on this system here. And the transfer function for that system is s plus 2 over s plus 5. Now, if we start by examining poles, remember we said that poles are the values of s that will cause the transfer function to become infinite. Now, if you remember your math theory, you're supposed to solve for this. You say, all right, uh, if I want my function to become infinite, I must make either the numerator infinity, or I could make the denominator tend to 0. So we could start with the latter. We could focus our attention here. All right, let me clear this a little bit. Focus our attention on the denominator. And so we would quickly recognize that if we wanted to make the function or the denominator tend to 0, then we could make s equal minus 5. Hope we're seeing that. And if s
Yes,
is
sir.
substituted, correct, if s is substituted in the polynomial, would see that the denominator becomes 0. Hence, even though we're learning that it is not mathematically sound to divide by 0, clearly in terms of limits, we recognize that when the s approaches -5, the function tends to infinity. Therefore, s equal minus 5 is a pole for the system shown. Now, when we look at the term for the definition for the 0, so the 0 is any value of s that will make the polynomial or the transfer function, sorry, become 0. So again, if you look at your math theory, if we want the function to become 0, we should focus our attention on the numerator. And so we could say, all right, what do we need to do to the numerator to make it equal to 0? And the answer shouldn't be far coming. S equal minus 2 will satisfy that condition. And so when s is equal to minus 2, the numerator is equal to 0. Hence, s equal minus 2 is a 0 for the system. So the system has a pole at -5 and a 0 at -2. Now, it is commonplace in control system theory and other disciplines of engineering, signals and systems or other type of um, system analysis field, to represent the pole zeros, the poles and zeros on an S-plane. Now, the S-plane is just simply a plane that has real and imaginary components, yes? And so we can now plot zeros using a bubble and we typically plot poles using a cross. So we'd see that there is a pole at -5, use a cross to represent that, and we have a 0 at -2, using a bubble to represent that. So that's a pole 0 plot, all right, for the system, pole 0 plot. And we're going to see a couple weeks from now that this pole 0 plot is going to become a very important part of the analysis of control systems, all right? Now, let's discuss stability. All right, we discussed stability in the first instance as being one of the design objectives. So there are three design objectives. One, the system need to respond timely. Two, it need to have minimum error, and thirdly, it need to be stable. All right, if the system not stable, you can't achieve that, to be frank, right? So let's just look at a simple definition for stability. And that definition says that a system is stable if a bounded input results in a bounded output. It's called the BIBO stability, right? BIBO, bounded input, bounded output. In other words, what it is saying here is that if you apply a finite input signal to your system, the system should respond with a finite output signal. If it does that, then the system is stable. But you might ask the question, then how can you ever have an infinite output response? That's a very relevant question. But what we're going to see is that if the system tends or wants to attain infinity, then we define it as being infinite. And we're going to see examples, or we're going to see a situation where the system is unstable. And you're going to see the system wanting to become as large as possibly can. Okay. So we'll come back to the BIBO stability discussion. But for now, this is one of the criteria for stability, the BIBO. Now, for a system to be stable, which is some important terms, for a system to be stable, all the roots of a very special equation called the characteristics equation, yes, must have negative real parts. It's going to be a very important term to remember when we are looking at systems, right? So for the system to be stable, we need to establish what on earth is this equation, characteristics equation, yes? And then we can say, okay, the poles of that, the roots of that equation must have negative real parts. All right, essentially we're saying the poles of the transfer function, okay? So let us continue to discuss this. When we talk about the characteristics equation, the characteristics equation is in fact the denominator of the transfer function, right? It's the denominator of the transfer function. That's called the characteristics equation. Now, why is it called the characteristics equation? It is so called the characteristics equation because it fully defines the nature of the system. So if you should take a model for a system as a transfer function and you extract from it the denominator, which again I say is the characteristics equation, that equation will fully describe the behavior of the system. Okay, that must be noted. So now let's continue with second order system response, and we're going to look at the different possibilities for system response. And we're going to do so using the poles. Remember now that the characteristics equation determines the behavior system, and say it another way, we could say the poles. Yes, the poles of the system, or the roots of the characteristic equation, is what we're going to use, or going to recognize rather, is what determines the nature of our second order system response. So let's start out looking at a situation where we have two distinct poles. That's one scenario, all right, one possibility. Yes, two distinct poles. Now, what are we looking at here? We're looking at the pole zero plot, real imaginary pole zero plot. And we are just drawing the poles. Now, be careful here. We're drawing the poles on one side. And you might notice on the plot that I have the term unstable here. Remember I said in the previous slide that for the system to be stable, what? All the poles, or should I say all the roots, same thing, must
Must have
have
negative real
negative.
values.
Thank you very much. Therefore, they must reside or they must be on the left-hand side of the imaginary axis. All right, that's important. So all the poles must be on the left-hand side of the imaginary axis. So therefore, this is a stable system. But in particular, the two poles they're real because they have no imaginary part. They're sitting on the real lines. They have negative real parts. All right, and they're distinct. What happens to a system in this case? In this case, we'd say the system is over damped. The system is over damped. And in addition to that, or should I say equivalent, we're saying a damping ratio, the damping constant is greater than 1. The damping constant is that factor that tells us how much damping is in a system. All right. And what we're going to recognize is that depending on the number, we'll see the system behaving in different ways. So once you have damping greater than 1, we say the system is over damped. And in a short while, we'll see what an overdamped system response looks like. Now, let's move on to another scenario. Let's look at what happens when we have repeated real poles. So there's no complex part to it, repeated real poles. And again, the poles are on the left-hand side of the imaginary axis. It's not about a stable system. Now, in such a case, the system is termed as critically damped. Yes, critically damped when both poles are the same. They're repeated real poles. In addition to that, or should I say equivalent, we could say that the damping ratio is equal to 1. Specifically, it is equal to 1 when the system is critically damped. All right, so just look at two scenarios where we have distinct poles, real poles that is, only. The system is overdamped. Here we're looking at the case where we have both poles being repeated and it's only real parts in the pole. So the system is critically
Critically down.
damped and zeta is equal to 1. Now let's look at the case where zeta, or should I say, let's look at the poles first. The poles are having complex parts, not just real part, but have both complex and real parts. Are we seeing that? Okay, so the coordinates for this point has imaginary components as well as real components. And there are two poles. All right, and poles occurs. What you're going to find is that complex poles that occur in what do you call it now again? Complex conjugate pairs. All right, complex conjugate. All right, they occur in pairs, complex conjugate. So they have the same real part, and then you have the complex part having plus and minus or negative and positive parts. Now let's come back to the scenario. So when we have poles that are having real parts that are complex poles with negative real parts, the system is termed as underdamped. It's underdamped. Let's take a look at what happens when the system is underdamped in terms of the damping ratio. The damping is less than 1. So as you see that the damping goes down, the system begins to get less damped. And we're going to see what happens to a system that becomes less damped. Okay, so we've just looked at 3 possible scenarios for a second order system. And we're talking about overdamp, critically damp, and underdamped. So let's continue. Oh, my thing just went here. So if my slide advance, all right, this. Just confirm that you're still hearing me.
Yes, sir.
All right, so my slide decided to stay on this one.
Yes, sir.
All right, thank you. All right. right, I need my slide to advance. All right, so not doing it that way. I am going to do something because it's not advancing here. Let's come back to here. Really? Okay, so I lost my slide. I'm back here. All right, let's pick this back up. So, are we all good? Are you still hearing me? I see my slides back up now.
Yes, sir.
Good. So let's go back to where things got frozen, or just before that. All right. All right. So here we're looking at the possibilities for the system. Now we're going to look at another possibility, and what I'm going to say to you here is that in control systems we don't consider this as something that we want to have happen. All right. This is not something that we count as one of the things that we would want to see happen. And this is what we call an undamped system. Can anybody guess what kind of behavior you expect on an undamped system? What do you expect to happen on an undamped system? Yes, go ahead, Buchanan.
Sir, we expect hysteria like you just keep going up and down, up and down, up and down.
Okay, so there's no once it's set in motion, it's not going to stop moving. That's correct. So if there's no damping, the system will just keep moving. All right, oscillation is what Alan is also saying. So you're gonna have constant oscillation. That is in fact very correct. So that's what happened. We don't want in control systems. There's no way that we could accept that as in a control, unless you design an oscillator. And it's not that we don't design oscillators unless it's a part of a control mechanism to keep the frequency of that oscillator constant. Then we monitor the frequency of it. All right. So what I'm doing here is to summarize the responses, and we would see the desired responses in the color. I don't know if you've seen it as being some kind of yellow orange. Please don't chastise me on color appropriateness. Anyway, so I'm talking about being under damp. Yes, that is okay. We're talking about being over damp, right? And in there we also have critically damp. So if I should separate them, critically damp, over damp. All right, somebody's microphone is open. You could close your mics, please. Thank you. So these are the possible situations that we could obtain. Please mute your mics, please, if you're not going to be responding to a question. All right, so this is okay for us, but we don't want a situation that is undamped and unstable. So we avoid being on the line, that is the imaginary axis. We avoid altogether. All right, that's unstable. We don't want that. We don't want that. Okay. Now here it is that I'm now summarizing the responses of the second order system. So we have undamped. Let us look at undamped, since that's the last thing that we looked at. Undamped, and as you rightly said, it oscillates. Constant amplitude. Once you stimulate that system, it is going to keep oscillating forever and ever, theoretically speaking. Now, when in reality, there's no such system that is totally, um, um, as far as I know it, there's no system that we can find that is without damping. So it will not stay in motion forever, but at some point in time, it will eventually settle down. So let's think about a pendulum that is set to swing in air. It will swing there for some time, but what is it that is going to happen? The damping effect of air resistance is going to bring that pendulum to rest eventually. Okay, so it would swing back and forth, but as the time progresses, the amplitude will diminish. Okay, let's look at under dump. Under dump is this one right here. We tend to mark on it. Under dump. All right, I'm going to draw another one for under dump that it could perhaps be more graphical. So it might look something like this. All right, under dump. So you have some oscillations taking place about the settling point. So again, I'm reminding us to mute our mics. Please to mute our mics. We're getting a feedback on the line here. Right. So underdamped systems exhibit oscillation. All right. So we see that oscillation going on right there. All right. Exhibit oscillations. Now, critically damped systems, they are falling between underdamp and overdamp. And interestingly, critically damped systems will have the shortest response time without oscillation. Yes, critically damped systems will have the shortest response time without oscillations. Okay, so the last one now is overdamped. Now, overdamped systems are very sluggish, take forever. All right, so it's very slow. All right, hope you can see that line here. They're very sluggish. Okay, and that's the graphical response for the different possibilities that we looked at for a second order system. Now, let me see if you're listening to me. Can a first order system oscillate? Can a first order system oscillate?
No, sir.
Cannot oscillate. Any particular reason?
Well, it behaves like critically damped, sir.
Okay. Well, even though we term the critically damped only for second order and systems above second order, so first order system cannot exhibit oscillatory behavior due to the nature of its transfer function, and even the nature, as I said, all first order systems look the same way. They look at the charging of a capacitor, and therefore we don't expect any losses. So you're quite right that it behaves, it has a shape that is similar to critically damped or overdamped system. But let me explain something. I'm glad you raised that point. For first order system, the response will typically look like this. I'm going to mark on the screen here. It will look like this. Note, put your attention to here, okay? In a system higher than first order, you're going to have a lag, a delay, and then you're going to have it doing this. So this is what distinguishes it. So if you look at a system response that resembles a first order system, take a look at the initial point. If it is moving with a very sharp gradient, then it's first order. If it has a if it has a lag, like what we're seeing here, this slowness or this I'm trying not to use the word lag because I didn't define lag. If it has this slowness to it, yes, or the steepness of the gradient is low, of course it will have to be this low. Then it's a higher order system. It's not first order. Okay, I
Okay,
hope that
sir.
is, yeah, man, cool. So let's continue to analyze. This might be a little bit small, but you can always zoom in on your personal device. Right? You can zoom in on the screen to get a better view as to what's happening. We're summarizing the effects of the poles and zeros, or should I say the poles, because we're talking about the effect of the pole, which remember I said the pole is what defines the characteristics of the system. Now here we're focusing our attention on what will happen, yes, if the pole begin to increase in complex parts. So the fixed part, sorry, the real part is fixed, and the complex component is increasing in magnitude. What would be the response? How would that change the response of the system? All right. Can anybody look at the plot and share with the group what do you observe? Can you extract the relationship, what is happening as the complex part of the pole increases. What effect it has on the system response? Again, you can zoom in on your device
Sir,
to.
so frequency increase.
I'm sorry, could you repeat for me?
Frequency increase, sir.
You're saying the frequency increases. All right.
At
All right.
F5.
All right. Good, good, good. While you're on the line, can you say if there's any changes? So right, I'm agreeing with you that there is a change in the frequency. And how do you recognize that, by the way?
Sure, because it takes less time to complete a full waveform, sir.
Less time to complete a full waveband. You want to explain on that, please? Takes less time. So we're looking at three scenarios, 1, 2, 3. And as you go from 1 to 3, the complex part increases. And you look at the plots. Hope you can distinguish the different plots, 1, 2, and 3. So for example, looking at 1 and compared to the other case, the other extreme, that is 3, what are you observing?
So amplitude difference, sir.
Amplitude difference. That's the peak overshoot. That's the peak overshoot, right?
Yes, sir.
Remember, good. But go back to frequency. What can you say about frequency in that respect?
Sure. Three take less time to have a complete waveform, as in to see a positive peak and a negative peak, sir, compared to 1.
Okay. So is it okay to say have more oscillations over the same period?
Yes, sir.
All right. Want to ask you one more question before you go. You remember talking about settling time?
Yes, sir.
Would you say that there's any difference in settling time?
Yes, sir. One settling time is, wait. Yes, sir. One settling time is shorter than 3 settling times, sir.
Where do you perceive? All right. Look carefully. All right. You want to be focusing your attention here. All right. And if I were to draw a line, I'm going to attempt to draw a line. Oops, not the best. Not the best. I'm going to come back here. If I could just bring my screen back down. Today my computer is.
So they look like the same, sir.
By the way, you're not seeing I'm zooming the screen, are you?
Yes, sir. I zoomed in and I'm seeing, sir.
So they're the same thing, right?
Yes, sir.
Good. So the settling time has not changed. That's where I'm going. The settling time has not changed. That's what is happening here. The settling time has not changed. That's what I wanted to recognize, okay? So that's what happened. Thank you very much for that feedback, all right? No pun intended there.
Yes,
All
sir.
right, so good. Let's move on to the other section here where we see what is happening here. Can somebody describe what is happening to the poles? What is happening to the poles? What is happening to the poles?
They are being reflected to the y-axis.
This thing what? Let's focus here. What is happening to the poles? The poles have the poles have real and negative part. I'm sorry, I keep saying that. The poles have real and imaginary parts. What is changing in the pole?
The real part, sir.
The what part?
Real part.
Okay, so the real part is becoming what? More negative, right? Becoming
Negative.
bigger. Yes, the size of it is increasing, but it's becoming more negative. If you understand what I'm saying, the magnitude is increasing, or I could say it's becoming more negative. What is the result of that? What is the result of that?
It becomes more stable.
It becomes more stable. Okay. Becomes more stable. Why would say what led you to that conclusion about being more stable?
Based on the, I think the definition you gave um earlier, it was like when you should have two poles in the negative, that should be negative. I'm not sure of the
Mhm.
definition.
It's a more stable, but there must be something that led it to say it's more stable. Oh, well, I see what you mean. Okay, so, well, I think you're going maybe from some interestingly more stable. You're actually right, you know. It becomes more stable the further away you move away from the imaginary axis, it becomes more stable. But I want to know, why you actually said that by just looking at the plot. I wanted to know what you were pulling away from it or taking away from it to come to that conclusion. But you are correct in that sense, but you still haven't shared with us how you determined that. But continue, go ahead, please.
Yeah,
Anything you want?
it was just the I think before the previous slide before this one, you're
Mhm.
indicating that once you have two poles in the negative direction of the real part, I think it's more stable.
Not recalling that, though, no. What I remember, but it's fine. What I did say though that once you have the poles on the left of the imaginary axis, then the system is stable. But I didn't speak to what
Yes, sir.
happened the further away you go away from the imaginary axis. But what I'm saying here is that what you said about stability is in fact correct. But I was concerned that I'm not sure how you were able to extract that from the plot. But having said that, though, anything you want to say about this response apart from what you already said?
No, sir.
All right, thank you for that feedback. I think there was a hand raised. Who was it? It's probably not seeing that anymore. What you would not recognize. By the way, anybody want to share what are they observing here? Because what we're establishing here is the effects of the pole on the system response. Go ahead, Jordan. I'm not hearing Jordan at all.
Oh, sorry. Sir, you hear me now, sir?
Yes, go ahead, please.
I was saying same thing. So the further away you go from the left, from the pole to the left, is the more
Let's get
stable
something
the
clear. Let's
system.
get something clear. Let's get something clear. The further you go away from where?
All right. So the further away you go from the imaginary line, sir,
Axis.
to the left, um, I would say you have a shorter settling time.
Absolutely. And how do you determine that, by the way?
Sir, because due to where one is and where two is, and then from the diagram on the left, sir, you can see that two settles before one.
All right, good. That's a very good observation. That's in fact correct. So the settling time is reduced the further away the pole goes from the imaginary axis. That's important. So here we're getting a feel as to the effect of the poles on the system response. So if you're looking at a number of transfer functions for a second order system, by examining the poles of that system, you can determine or you can compare the system response. Okay. Now the third is a little bit, well, it's a summary of the first two. You're increasing in complex part as well as increasing in real part, and you can see the two are combined. So if it will have increased oscillations, however it will settle faster. Okay, so that's basically summarizing the effects of the poles and their position. All right, we're going to seek to close off with another stability assessment here using the Rothe-Howitz stability method. Now, what is police here is that when we have a system, and if the order of the characteristic equation rather is greater than 4, meaning that the polynomial is of power of order higher than 4, it's going to be really difficult for us to determine the roots and to make this assessment. As I said to you before, by examining the position of the poles, you can say, okay, this system is going to exhibit this behavior, that behavior, and so forth. Now, once you get above fourth order, it becomes difficult to extract roots, well, by hand, that is, okay? And as I would say to you before, as I've said to you before, um, in today's time and age, we have software that can easily compute these roots, all right? easily compute the root. So this I'm going to be frank with, is just mere academics and just to appreciate the analysis tools. But the truth is, you never use this tool. I can't see any reason for you to use this tool going forward when you have apps on your phone and you have software that can compute these. That said, let us move into what this whole root Howitz stability thing is. And this is what they'd have used in the earlier times without these high computational computers and so on. All right, so the work of Root, Root in 1905, excuse me, and Howitz in 1875. These are two independent researchers, two independent scientists. They combine the work, and it gives us a method to determine the presence and the number of unstable roots. Now, the root table allows us to determine the stability of a single input, single output linear time invariant system without knowing the roots. So we can actually determine how many roots are in violation, that is, how many roots are on the right-hand side of the imaginary axis, and as well as we can obviously tell that if it's unstable. That's what this root table is going to do for us. Now, here's the criterion. A necessary and sufficient condition for stability is that all elements of the first column of the root table be positive. That's simple. Necessary and sufficient condition for stability is that all the elements of the first column of the root table be positive. Now, the number of roots with positive real parts is equal to the number of sign change in the first column of the root table. Let's go again. The number of roots with positive real parts, the number of roots that are on the right-hand side of the imaginary axis, is equal to the number of sign change in the first column of the root table. All right, let's see how we establish this. So now let's look at a general format of polynomial. So we're not concerned with the numerator. So just simply put capital N of S. Whatever that is, it's not important. And we're focusing our attention on the denominator. So here we're seeing that the characteristic equation is this equation here, and we're just taking it out and put it right here. Okay, so set it equal to 0, and we're going to learn now how to extract these coefficients. And now watch this carefully. What we're going to do is to create the first two rows in our root table. And what we're actually going to be doing, let's see if I have it summarized in the next slide, using the coefficients of the polynomial. So let's look at some. We're going to use this. The first coefficient would be the coefficient of the highest term in the polynomial, that is s to the fourth. So a4 would be the first element in the first row, and what we'll do is to skip the next term. So the next term is s to the 3. Good. So we skip that and go to s to the 2. So the next term is a2. And then we skip again and we go to the next one. Now be careful. We're going to see that if s to the third wasn't there, meaning you wouldn't see anything. It simply means that the coefficient would be 0, so you have to acknowledge that. Okay? So bear it in mind as we go along. So we're going to be taking the elements for the first row, and here's how we do it. This one, go to s to the 2 here, s to the 0, which is here. So a4, a2, and a0 would form the coefficients, or would form the elements in the first row. The next row now would be consistent, would consist of a3, a1, and 0. Or we could just keep it like that. Let's look at what happens next. So you see it here, a4, a2, a0, a3, a1, 0. All right. So we have just established the first two rows in our root table. All right, first two rows. Now what's next? It gets a little bit interesting here. The next step now is summarize here. Okay. Next step is summarize here. Let's see if I can zoom this in a little bit. Oh, all right. So, can somebody describe what is happening right here? What does this mean? Let me see if I get my pen back. What does this mean? What does this mean? That part. Anybody describe that for me? Interesting. I won't repeat what Travis just text. Anybody can just, let's take it in part. We're talking about right here. What does this mean? Nobody? Go ahead, Buchanan.
Is that, sorry, is that determinant?
The determinant, continue, determinant of the matrix defined by A4, A2, A3, A1. All right, that's correct. And so how do you treat that when you say the determinant?
That would be,
Interestingly though, go ahead, go ahead.
I was going to say that would be A4 times A1 minus A2 times A3.
Okay. All right. If A4 times A1 minus A3 times A2. All right. All right. Put it this way. What we're going to do for some person, I'm not sure if you did this because I'm not going to teach the math here, but I'll teach the procedure. All right. And some in the math one or math two, not sure exactly where you would do this, but what is happening here is that, and it's going to be summarized in the next slide, is that we are looking at the elements in the first row and we're going to use it to populate the other rows. So we have to look at the rows, and I'm going to show you look at rows in one format. So we're looking at the rows like this. Always the first two elements in the leftmost column paired with this one to form what is here. Are we seeing that? Then for here, what are we doing? Oops, what just happened here? And for here, yes, what we're doing is to again start with this one and then skip to the next column. Are we seeing it in here? And for the one over here, we always again start with this one. Let's clean this first. Start with this one. And then we use the next one. So we use the one that is over here. Obviously over here is 0, 0, and hence it looks like that. Now, let us see if we can see the consistency. We're taking it in strides, all right? Let's come down now to this row. Let's say we populate up here accordingly. What do you suppose that we're going to be using? All right, we're focusing our attention here. We're going to use these two elements, A3 and B1, and they're going to always occur in all the rows going across, okay? A3 and B1. See it occurring here, A3, B1, A3, B1, A3, B1. Then what? For the first one, you're going to use A1 and B2. Here we go. How about this, the one that follows it here? We're going to use what is in the next or the adjacent column to the right, which is going to be 0 and 0. All right, and so we're seeing it here. How about the one here? If we skip and go to the one over here, that's nothing there, so we put 0, 0. Again, we're going to continue going downwards. We're going to see what should happen next. So we now have this. So we now have this last row to populate. All right, and there's going to be a number of rows equal to the order of the polynomial. All right, plus 1. All right. So in fact, should I say it will equal to the number of elements, I should say rather, the number of elements in the polynomial, which is equal to the power plus 1. Okay, S0 to 4. So the last element here would be using these two terms, B1 and C1, for the first element here, it occurs throughout. And again, you go on using this for the first one, then you skip this one for the second one, and then you skip, and then whatever is here, 0, 0 for the third one. So let's look at this in another way, or summarize another way. What we're actually doing to form B1, what we're doing is we are using the product of an minus 1. Let's look at what this is, or we interpret this. An minus 1 times an minus 2 minus an times an minus 3 all over an minus 1. Right, the term right here. Okay, so we're going to have to remember that. All right, so we'll leave it there for a while for you to sort of, appreciate how to interpret that. So it's the negative, and some persons don't understand the term turbulent, so I'm not going to teach the math term, but just to be able to extract it. So if you look at the polynomial, you are able just to look at the terms and know how to treat with them. All right. So it's the negative. All right. Let me go to an example. Let's come back up to. Excuse me. Let's come back up to the previous slide. So what then would B1 be? All right. Can somebody tell me what B1 would be? Based on what we're just looking at before. Can anybody remember? What do you want to comment? All right. So let us look at it. So here it is. What we're going to do. I wish somebody could at least start so I could see where to proceed. But this is what you have to look at and begin to appreciate for yourself. So what we're going to do is that we're going to have the negative. I'm going to see if I could write here. Where's my pencil? Let's extract here. Space. We're going to have the negative of A4 A1 minus A2. This is not a Q. A2 A3 over A3. All right. So what does this equate to? It just simply comes down to Q. What did I see? What I'm talking about with Q now? A2 A3 minus A4 A1 over A3. All right. So that's what it comes down to. All right. So we're going to now attempt a problem by looking at this. And note that each time what we're dividing by is the term here. We're dividing each time by the term, the leading term. You just have to look at it and try and remember. So each in the row below, you're dividing throughout by the term that is to the left, far left here. So if you look at this row here, let's look at this row here. What are we dividing by? B1, all throughout by B1. For here, what are we dividing by? All terms by C1. So we're going to attempt to do this, and we're going to take our time to establish the rules to do this. All right, so we're doing a root table. So determine whether the system with characteristic equation s to the 4 plus 2s cubed plus 3s squared plus 4s plus 5 is the system stable. All right, is the system stable? So the first aspect shouldn't be difficult for you. That is how you select the elements in the first two rows. So we should be able to do that. Anybody having difficulty establishing the elements in the first two row?
No, sir.
All right, so one person. Out the door. All right, so for completeness, we're going to go through it. So we start with the highest term in the polynomial, s to the fourth. Then we skip s to the 3, go to s to the 2, skip s to the 2, go to s to the naught. That's s raised to the power of 0. And we put in the coefficients. So this is 1, this is 3, and this is 5. And that's quite fine. And then now for the second row, we have 2, and we have 4, and then we just pad here with 0 if we need to, right? We just pad with 0. So the first two rows, quite easy, no problem there. Now comes the exciting part. How do we determine the first element in the third row? First element in the third row. So remember what we're going to do. We're going to use this, and then we're going to divide it by the term here. All right. So when we're using the elements here, we have to remember what to do now. You know, it's the negative of what we have here divided by 2. And by the way, it's in terms of the determinant. That's a term I didn't want to use. But what we're going to do, if in the absence of saying that, is to look at the opposing diagonal and do the subtraction. All right. So it's going to be. Let's see if we could erase this. And so let's see if it works out to be. And right in, yes, it is. Let's see if it works out to be 3 times 2 minus 4 all over 2. So that's that. 6 minus 4, that's 2. Divided by 2, that's equal to 1. And so we got lucky. Is that okay?
Yes, sir.
How about this term here now? So what we're going to be focusing again is we're going to have to keep this, skip this one, and go to here. Put a 0 there. So again, watch carefully what we're doing. We're using the opposing diagonal. We're going to go 5 times 2. 5 times 2 minus 0
0.
times 1, which is 0, all divided by what? Remember, it's the
2.
same term each time, 2. So that is going to be what now? 10 minus 0 over 2. That's going to be 5.
5.
Wait, we got lucky again. All right, and so that would complete the second row. I mean, you could part the other sections with 0, because clearly if you continue to go there, you're going to end up with 0. So that is quite fine at this stage. Okay, the next move, I'm in a meeting here. Can you go back out, please? Sorry about that. So here we're going to go to the next row. So I need to clean this. Right, so let's go to the next row, which is here. So what are we focusing our attention on? We're looking at this element, and here. So opposing diagonal, that would be 5 times 2, and I'm doing this for the purpose that persons can follow. 5 times 2 minus, so this is the
4 times 1.
Minus 4 times 1, all divided by what?
1.
Correct. So that's going to be what? 10 minus 4, that's 6. Let's do this correct. Oh, let me see if I'm doing this right now. Opposing diagonal, that is 5 times 2 minus 4 times 1. No, I did not use the opposing diagonal. That is the leading diagonal. I did say opposing, and I used the leading diagonal. Opposing diagonal meaning this one. We start with this one first. So let me erase all of this thing here. And this is the practice that you would want to do to ensure that we're understanding this, what's happening. So again, we're talking about here and here, and we're dividing by this. Leading diagonal is this one. We're not using that. Using the opposing diagonal. That's a term used in math, by the way. I do this math here a long time, you know. It's very quiet. Only a few persons talking. So we're not using the leading diagonal, using the other one. So it's going to be 4 minus 10. That's 4 times 1 minus 2 times 5. All divided by 1. So that's going to give us minus 6. And so here we have our minus 6. For the next element, we're going to now take the 2 and the 1. So it's going to be 2, 1, and 0, 0. And again, we're going to be divided by that. What happened here? We can say it's going to come down to be 0. 2
Yes,
times
sir.
0 minus 1 times, that's 0. So that's all good right here. Again, I'm going to clean the slide, and we're going to do the last row. Last row. All right, the last row is here. What are we doing? We're taking this, and we're
1,
going to
5,
divide by
minus
that.
6, and 0.
So what will be the first element? Opposing diagonal. 5 times
So
minus 6.
5 times minus 6.
All right, so that's
Minus
minus 30. Minus 0. All divided by?
minus 6.
Correct.
So
All
it'll be
right, and that's
5.
going to give us positive 5.
Yes, sir.
Now, what can we say having done all of this? Now, we just complete the root table. What can we conclude? So we'll focus our attention on the first column, okay? And we
Yes,
said
sir.
that if a necessary and sufficient condition is that all the elements in the column be what? Be
Um,
positive, all right? They be positive. For the system to be stable, all the elements in the first column must be positive. Now, we would recognize that there is one element in the first column is negative, therefore the system is unstable.
unstable.
We can go even further to say, all right, how many roots are in violation? So if we go from top to bottom, we say positive, positive, positive. Here we have a negative. That's one sign change here. And then we move back here to positive. So that's 2 sign changes, 1, 2. Hence, there are 2 poles that are on the right-hand side of the imaginary axis. 2 poles are in violation here. That's what the root table has just helped us to establish without finding the roots of the polynomial. All right. And this is for 4 other system, but you can do it for as high as you want to go, you know, by just simply doing that simple 2 by 2 manipulation. I'm talking about the matrix now, right? As opposed to find the root of a 6th order, 7th order, 8th order polynomial. Okay. All right. So here we're going to see how we can use this. Might say, why are we actually even doing this in the first place when we have computers? Same story I tell you before, but we're going to show how we can actually use this root table to do a design problem. No computers. All right. So here it is that we have a system, and it is a closed loop system. Okay. It's a question for you now. What is the transfer function for the forward path? What is the transfer function for the forward path? That's a question for you. See if my students are still here. Well, I see 26 of them here. Oh, they're not sleeping.
No, sir. K
Go ahead, please. K.
KES over S into S plus 1 times S plus 11.
Why did you say KES?
Well, if we look at the node, we can see that ES is going into the well on this, sir.
Mm-hmm.
Okay, transfer function will be k over s into s plus 7, s plus 11.
Mm-hmm. All right. So please note that. All right. So we don't. Thanks for the feedback, both of you. Thanks for the feedback. So we don't consider it signals that are going in or out. We don't. We just simply look on what describes the block, and what describes the block is what is inside here, which is the transfer function. All right. So I want to remember that. Okay. Now,
Yes, sir.
having said that, good. Now, having said that, now we want to apply the root table, sorry, the root design criteria, right? The root Hobbit's method. or the root table analysis to design a system, yes, determine the value of k, yes, for which the system is stable. So as a designer, whatever the system is, we're not concerned about the system, whatever it is, if it's a suspension system, it's a drone or whatever, we don't care right now. But what we do understand is that as the designer, we have control over a particular parameter called k. We can actually set that. And what we want to do is to set k such that the system is stable. Quite likely, there are going to be some values of k that will make the system unstable, and we don't want that. So we're going to do what? Avoid those values of k. All right. So remember what the table spoke about. It spoke about the characteristic equation. So can you tell me how then do we get the characteristic equation? What do we need to do?
Just expand
What
the denominator, sir.
expand the denominator talking about this time here? Where's my pen? Expand this?
Yes, sir.
Okay, stay in line for me. You're expanding the denominator, and that would give you the denominator for what?
Oh,
This entire.
that would give you the characteristic equation.
You sure?
Yes, sir.
All right, don't
Um,
move, don't move, don't move, don't move, don't move. So are you suggesting that this forward path transfer function is the same as if when you simplify this entire gizmo here? Please pardon my term, but whatever this thing here is, we're just treating it as some little things. So what we can appreciate, by the way, you're supposed to know by now that this is not any little thing. It's supposed to can simplify it, which means you use one block to represent everything that is inside here. Now, what I'm trying to get your attention on is that when you pick out this expression and call it the characteristic equation, it is not entire. It is not true, because this expression here in the block is not what describes what is in this bigger block. Are you able to see that?
oh, yes, sir.
So therefore, we have to do some gymnastics to get that to the appropriate point. Any ideas? What is the gymnastics? I guess the gym is closed now.
So you can probably do something name. You have like A over S plus B over S plus 7 plus C over S plus 1. And you find the values them are A, B, and C. I don't know if that make any sense. I don't remember the particular. Is it partial fraction? I'm not sure. No.
That's a lot of gymnastics, but it's not in the gym that it's supposed to be at all. Wrong gym. So partial fraction. Remember, we're talking about a feedback loop. How do we? Let's call this G. If we can't juggle the bell, maybe it's the time of day. The time of day. The time of day. All right. The time of day is time now for cool off and take a break.
Would you like to move the summing point or something?
You see what I'm talking about? I'm now confirming that you have. I used to have a session. I'm not going to talk to them because I'm recording a session where a student would tell me that once the class get to about an hour 20 minutes, the student will put up his hand and remind me that we have now exceeded the threshold time, which means that what you say beyond that point, there's a high probability it will not be received because you have reached the threshold. So I'm definitely past the threshold. All right. Boy. What are you saying, Travis?
Sir, we student that, sir.
Hello?
Sir, we student that, sir. You want me that?
No, it's not in this group. It's a student I had some years ago. Every class, once I get to 120, I had to stop and give. That time used to have the session running for 3 hours in a row. 2 hours lecture and 1 hour tutorial following that. And so he would stop me at 120 thereabout. But please don't try because I'm not going to stop. right? And say, remember, there's a threshold. Religiously, I'm not joking either. I'm not joking. So once I see him end up, I say, okay, now it's a good time to stop the class, take a break, 5 minutes, and come back in. So here it is. I'm seeing evidence of a threshold because I'm hearing all different kinds of things except the right thing. Last week, I believe, no, it wasn't last week. The week before, we discussed the rules for simplifying a block diagram. And the last we looked on was the feedback loop. And somewhere in there, you should remember that to simplify this, if you call this entire block G, it'll be G over, because it's a negative feedback, 1 plus G times 1, because the feedback block here is just 1. But remember that if it was H, it would call GH. But remember that? Uh-oh.
Yes,
Yes,
sir.
yes, sir.
All right, only one person up and running. All right, so long and short is that you're going to have to simplify this, you see? Get one block. And so I'm hoping that that was done in the second slide. So when you simplify that block, whatever gymnastics except you need to do the right gymnastics, by the way. So let me see if I can do this quickly. You're going to have to expand this, and whichever way you do it, whether you're going to do the closed loop thing first, then expand or expand after, it doesn't matter. But what you're going to end up with is this expression here as the characteristic equation. Good? That is going to be the characteristic equation. If you don't get through to that part, you're going to have problems. So you should be practicing. Um, uh, you should be practicing. All right, I'll speak about the assessment after in a few. So I'm going to put the short letter go to the discussion of that. So that is the characteristic equation, and it's not difficult to populate the first two rows with that polynomial. So the first element is going to be 1 because the coefficient of s cubed. Skip that, go to s to the 1, and that becomes 77. And then you move to the next row. So it's going to be 18 and k. All right. And we're seeing that. Now here is the fun part where you now need to populate the rows below it. Now this is a very simple polynomial. It's a very simple, it's a third order polynomial. It could be a fifth order, it could be a 6, 7, 8, 9, and so on, but it's simple, third order. So
That not wrong.
what is wrong, sir?
The minus sign missing.
From what?
S1.
S1?
Yeah, the
All right.
first.
We're going to see. We're going to see. It's a possibility, like everybody else, I can too make errors. So let us see if I'm in fact having an error there. So we have, do you agree that the first two rows are populated correctly?
Yes,
So
sir.
in content. All right, thank you. And then somebody say yes. All right, thanks, Travis. So moving along. So let us now proceed to populate the row below. So we're going to use these two. Again, we're using the lagging diagonal. That's the term you use, but for now, let's work with it. So that's 18 times 77. Run it through your calculator and tell me if that's what you get.
Yes, sir.
Minus the leading diagonal. So it's that minus k all divided by the first element, which is 18. So based on what we had discussed before, that seems consistent. Any concerns with that?
Wouldn't
No, sir.
everything be negative?
Could you go again, please?
I
I
thought you
hear a
had to
comment
take
in the back.
I thought you had to take the negative of all of that.
No, man. Remember, that's why I said practice the way that you can best appreciate it. What we do, as I stop using that term, what we do, I didn't want to use the word modulus or the determinant of the matrix, because I figured that some persons in the group are not familiar with that, and I don't intend to teach math in a controls class. So I'm saying to you, whenever you see the expression, just simply do this. All right, simply do this to your matrix, and what you're going to do is take the not the leading diagonal. This is the leading diagonal. Not going to take that one. You're going to use this one. So that's 77 times 18 minus the leading diagonal. Yes, all divided by this element, and that would be sufficient. If you want to go and investigate after, and I suggest you strongly do so, what exactly this term means. When you say A, B, C, D, this is the elements in the matrix, and what does that mean? So look that up for me as you read additionally, and you can have a more fulsome understanding. But for now,
Sir, I'm sure if you go back in the notes, when we're doing the calculations, we were using the minus sign in front of that thing.
yes, but why are we doing that? Let me explain to you what we're doing that. Let's see if it can
Yeah,
make sense.
because when we're working it out, we had
Hold
used the
on.
minus sign.
No, 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 no. We weren't doing it like that. I'm
I'm
surprised somebody
confused.
just waking up. All right, let me ask. Is there anybody else who is having an issue with how I'm doing it right now?
No,
No,
sir, it's perfectly fine how you're doing it.
Somebody just wake up. We have been
No,
going through a
but
couple. Go ahead.
No, what happened is I
sir,
thought I was following along.
No, what I'm saying, if you were to use, there's a term in math. I'm not going to go into that. That define what this means.
Sir, no, it's not that. Go back. If you go back to the other
well, man,
slide,
that's what I mean, sir. In the
there's a
previous one,
negative
there's a
sign.
minus sign.
Go
What
back to
negative
where?
sign?
Yeah, yeah.
No,
Right
no,
at
no,
the
no.
top.
Let's be calm.
The
Let's be
negative
calm.
sign. Just
Let's be calm.
the negative sign. Why are we
Where should I
ignoring
go?
that now?
Where should I go?
It's you're right there. Calculation
Mm-hmm.
of table elements. That
Mm-hmm.
negative sign. Why are we ignoring it? I'm saying when you do that, should we multiply through with the negative sign?
To what?
That
Hmm. Do you know
right
what
there?
this means? Do you know what this means in here? As I asked the question before, do you know what
Yeah,
it means? What does it mean?
yeah, I know what that means. It
What
means
it
that
means?
you're going to multiply the leading diagonal and then minus the opposing diagonal, right?
Correct. Now, if the opposite way, which means to subtract the opposing diagonal from the leading diagonal, it's the same story. So instead of me explaining how we derive or what this means mathematically speaking, I was saying in all the subsequent explanations, and you can go back and look at it in the video, right? I did it here. In fact, we were doing it here. So I'm asking if persons were asleep. When we were looking at it here, what were we doing? Say, okay, let's take the not the leading, but the lagging. Don't know what term you use, but this is the leading diagonal. You take this one, 3 times 2 minus 4. So it's 6 minus 4, all divided by this element. And what did we get? We ended up with 4 divided by 2. All
All right. So you were okay, I get it now. Thank you.
right,
Because I
cool.
was doing it the other way and then minusing after.
Same story we end up with.
Yeah.
All right, same destination. So come here now, we're doing it. And again, I'm saying if you do it the way that you're comfortable with, if you can appreciate what that means, I'm just using what at this point would be best if you don't appreciate what the term here, A, B, C, D means. All right. Simple mathematical term, but I don't wish to teach that right now. But I could say to you, whenever you have your polynomial, if you have your table, just simply do this. Take the you have the leading diagonal, you're going to take that one first. Take this one, find the product, and then subtract the leading diagonal from it. So it's 77 times 18 minus k, all divided by this term, just to keep it simple. And we do the same thing again. For this term right here, in fact, there's no term there, but so we move on. Move on to here. What are we taking? In fact, this is 0. We're taking here and here. I'm going to clean this up. We take it here and here, dividing it by this term here. So what do we do? Again, we have to go to the diagonal is not leading, right? So it's 18 times 0 minus, it, of course, that's going to be 0. 0 minus k times 1386 minus k over 18, all divided by, let's see if I'm doing this right now, all divided by k. Is that correct? Good. All divided by k. This is the term we're going to divide by now. Let me go back one more time.
sorry,
We're not dividing by k, divide
sorry.
by this term. We're dividing by, second, please. We're dividing by this term here. All right. So divide by, and I don't have enough space to put it back, but obviously you're going to say we divide it here, you're going to end up with, we're going to end up with, what do we end up with here? Do we have negative? Let's do this one more time. I'm coming to your question, please. Just give me a minute. All right. So that. Clean this up and do one more time. So what we're doing here, we want to establish the term here. All right. So we're using the matrix here. All right. Login diagonal is here. I'm sorry, I keep doing that all the time. Let's go one more time with this. All right. Let's go slowly here. So we're not taking the leading diagonal. Hence, this is what we're taking first, the product of that first. Yes. Then we subtract it from the leading diagonal, then divide it by the term here. And you can clearly see that the result will be K. There's a comment or a question. Could you go ahead, please?
Never mind, sir. You clarified. You clarified.
All right, thank you. So I'm hoping that we can see that the table is complete in so doing. As it is here, it is complete. If there are any questions at this moment, please indicate quickly, please, quickly. All right, so that is okay. Now for the system to be stable, what did we say about the first column? What did we say about the first column?
Positive.
Sorry, positive, which means that this element here, which has a variable in it, must be greater than 0. It's the same thing as meaning positive, don't it? Whatever
Yes,
it is, it must be greater than 0. And it also means a K here, so must be greater than 0. Two conditions. And all we're doing next is to express it as a simple inequality equation. So K must fall between 0 and 1,386 for the system to be stable. That's how we just do a design. So whatever you do, keep K away from 1,386 and keep it away from 0. Story is complete in that respect. All right, so that is the last slide. I'm hoping that we're able to recognize the ability or the ability of the root table to analyze systems without the need for computer or any sort of machines, all right, or calculators. All right, so you're required to do analysis of system using the root table. All right, so any questions at this moment? We're going to close off. Any questions? Go ahead, please, Jordan.
Yes, sir. It's not related to the slides here, but regarding to last week.
Hold on. One second. Just let's take the ones for the slide first, and then we can proceed. So if there are no other questions related, there are no questions related to the slide, then we're going to stop now. All right. So.